So my name is David Walls. I'm a PhD researcher at the University of Strathclyde, and I also work with Tyne Rock Energy in the Mine Water Geothermal department. This talk is on a portion of my PhD, which covers the Mine Water Geothermal Resource Atlas for Scotland. First of all, so thanks to EPSRC and John Mather Trust for funding, to the Coal Authority for sharing ample amount of data that's gone into this work, and for also allowing me to make this openly available and free to anybody who wants to view it. To the Improvement Service for hosting this on their Spatial Hub website, to Tyne Rock Energy for some industrial steerage on what would make this most applicable to industry, and to Dave Banks, Neil Burnside, Yannick Kramer, and Adrian Boyce for supervision and support. Just to give some context, we're staying in Scotland for this one. We are looking at the Scottish coalfields overall, which are highlighted in blue. Change that to laser, sorry. And you can see without any GIS analysis, overlap is with the main population densities in Scotland. So this talk will cover my overall PhD aim. Then we'll look at what the 4 geofactors that we've outlined are, which influence the final output. And then we'll have a quick look at how we can access this online and how I would like you to share it with me, please. So let's get into it. The overall aim of my thesis is to find out where the best places in Scotland are for mine water geothermal energy. And on the right there with the image in the figure, this in part is due to the surface resources which are available, i.e. through gravity drainages, or through Coal Authority treatment sites, which I think there's a talk about later on. And I've characterised these as best I can across Scotland and quantified them for their heat availability. So not what this talk is on, but remember that figure because it will come into use later on. What we're talking about today is the subsurface resources. So where in Scotland do the underground mines pose the best geothermal energy potential. An informal aim of my PhD is basically to help the geothermal industry get more projects started. And quickly, what I mean by best in this case is projects that are going to work, projects that have competitive capital expenditure costs, and projects that have competitive operational expenditure costs. So straight into the geofactors then. First of all, we're looking for areas that have 2 or more overlapping mine seams. And this has come from data from the Coal Authority, where they've digitized their mine abandonment plans, and I've processed these to show where they overlap. In addition to this, we also want areas where there are no shallow seams, and this again has come from the Coal Authority's data set for their shallow workings. So why are these 2 things what we're looking for? First of all, number 1 there gives us a rough proxy for resource size, but also where you can sort of prove that you can drill into one coal seam for an abstraction well and re-inject into a different coal seam, and that minimizes your risk of thermal feedback. And number 2, no shallow seams avoids the subsidence risk, and they've got a blanket value of 30 meters from surface level anywhere that's a shallow seam. So a quick schematic at the bottom there, you've got 3 mines overlapping in some places but not in others. And then you have an area of shallow mines which we can remove. And overall for Scotland, that produces a diagram that looks like this. And so in the dark red there, you have areas with overlapping, and they are going to be taken forward to our final output map. And the areas where it's pink is a single seam, and that's going to be removed. Already from this map, we have removed anywhere where there's shallow workings. Number 3. Is a suitable mine water table, and I've selected 0 to 60 meters. This has come from water level data from the Coal Authority's borehole or shaft monitoring points, but also those discharge locations which we identified. What we can do then is that map on the left is we can create a mine water level surface which spans the whole of the Midland Valley. And then we can subtract that absolute value from the surface elevation model, and that will give us depth to mine water head. And these are the values that are going to be useful because with different depth to mine water head, you have different electricity costs for pumping your mine water. Some of them are coloured in pink, and that's where the water level I've estimated is between surface and 20 metres, which might need extra consideration for your re-injection capacity. If your transmissivity values are good, then there'll be no issue. If the transmissivity values are less good, then you might be limited with how much you can. This, of course, is all subject to how much data we have, and it's fairly sparse on the west coast of Scotland, but fairly resolute in East Lothian and Fife up on the east side. There might be some changes with water table recovery, or there might be some new systems come online, and you might be dealing with some dynamic heads instead of static water levels. Finally, then, finally is number 4, which is a reasonable drill depth. And for this, I've selected between 30 meters, which is where the shallow seams end, and 250 meters. Again, we go back to what is best here, and we've characterized it as a competitive capex for installation. So we're looking at how much does this cost to drill. And with data internal to Rock Energy, they've shown that anything greater than 250 meters needs a bigger rig, and they charge more per meter drill. So we've just taken that as a cutoff point, and we're going to take forward anything that's shallower than 2 meters. Yes, I agree that depth roughly equals temperature, as Malem showed yesterday. So this means that we're potentially screening out any areas with the greatest temperature, but we're looking at sort of creating these competitive CapEx and OpEx projects to get them off the ground. So there's our 3 different maps made up of 4 different criteria, and we combine them all together to find one final map that shows areas of overlapping seams with no shallow seams, a drill depth within 250 meters of the surface, and a ranking system based on the depth to the mine water, which we continue over to color our map. And it looks something like this. So here you can see the biggest bulk of area is sort of in the central coalfield around Motherwell, but there's feasible areas all through Fife, through Lothians, through Ayrshire coalfield, and even in Stirling and Clackmannanshire. And so why is this useful? Well, first of all, hopefully it's going to raise awareness of mine water geothermal energy to audiences who are out with this community and don't know about it. And that means it can be incorporated into some of the early stage planning applications. It also means that you're going to save money on your project because there's no need for technical experts right from the start. However, I would caveat that by saying, please don't use this to inform where you're going to put boreholes in the ground, because you still will need technical experts at some point, whether that's to fully characterize the resource you have available, which we've seen many presentations doing so far, or to kind of inform what's going to be your best drilling targets. So it's very much that first pass screening tool for projects just to get a little bit of momentum. What can we do beyond that? We're going to zoom in, and I've done this in the supplementary material of my thesis, but it'll also be supplementary material in the publication that we're going to bring out. And it will show individual local authority areas with the MIRAS, the Mine Water Resource Atlas for Scotland, broken down to each of these local authorities with these surface resources overlaid. So this is North Lanarkshire with the greatest area coverage by the MIRAS. And that's just sort of like a bit more nitty-gritty for us to see where these resources really are. As of Tuesday, on the Spatial Hub preview map, and you can simply access that by Googling that phrase, and then click on the little layers icon, and then scroll down to M for Mine Water Geothermal Resource Atlas for Scotland. Select that, and you'll be able to scroll in and out, go and find your house, go and find a project which is associated with you. And this is really crucial, I think, for local authorities, planners, landowners, and developers. And I tried to visualize what this could do. And essentially what I've decided is that beforehand, you needed somebody who was passionate about it, somebody who knew about it. You probably needed a geologist on board, an engineer, a landowner, and a developer in order to get this project off the ground. Now, and a little bit more simple, hopefully you just have any of those from above who bring a bit of passion, and they know about this screening tool, and they can just use it, and that's enough to get a project at least to the idea stage to be brought forward to feasibility studies. So in conclusion, number one, there's a new atlas showing the best mine water geothermal resources in Scotland. Number two, it's freely available for anyone to view on the Spatial Hub preview map. And number three, please share this. Share this with anyone you think has any jurisdiction over projects, or any of your mates who are planners, or anyone you know in local authorities, etc. Just sing the message loud and wide. And so finally, a quick thank you for listening, and to share that I'm willing to take any questions on this either now, or if you're looking at the data and you want to get clear on what it shows. And also a shout out to some of the international mine water geothermal systems around. It was at this conference last year that I made a plea for these people to host me at their sites when I cycled across Europe in summer. So we heard from Florian yesterday. This is the site in Bochum. And we heard from Luis yesterday at the site in Mieres in Spain. So thanks for both for hosting me. And yeah, looking forward to hearing what updates come in a year from now.